Welcome to the lecture on assessment of discretization schemes. So, in the last lecture we talked about the traits of the different type of discretization schemes. We talked about the upwind differencing scheme, we talked about the hybrid differencing scheme, power law scheme, and even the quick scheme. So, in this lecture we will try to understand by by looking into a problem, and we will see that how they are solved and how we get the solution, how these results which we get by using these differencing schemes for different cases, especially when you have the variation of the Peclet number because of the convection component. So, how the different differencing schemes they are able to predict the result, and that how they match with the analytical result. So, that we will see in this lecture. So, we will talk about a problem. So, that in a problem, in that we have a property phi which are that is transported by means of the convection and diffusion. So, for this phi and that is for a one dimensional case. So, so it is a problem through of the convection and diffusion through one dimensional domain, and so you have this way your phi is transported, and you have the conditions which is given. Now, your u is in this direction. Now, here this is your x is 0 and this is x is 1, and the value of phi, it is taken as 1 at this end, and it is taken as 0 at this end. So, these are the two boundary conditions. So, you have so boundary conditions are phi 0 is 1 and phi 1 is so this is at x equal to 0, and then you have phi L will be 0 at x equal to L. So, this is the boundary condition. Now, what happens that in this case we will see that how we find the control volume. So, we will have the number of control volumes in this domain, and then we will try to assess that how the different schemes they are able to predict the result which is, and how much it is close to the analytical result. And we are going to have that. So, we are going to have the calculate the distribution of phi and as a function of x, and for the two case, and in one case we are taking u as 0.1 meter per second, and in the another case we are taking the u as 2.5 meter per second. So, these are the two cases, and as you see that your length is given as 1 meter, rho is 1 kg per meter cube, and tau is given as 0.1 kg per meter second. So, this way you have these values. So, that will be used for finding the f and d, and the first job will be to have the to have the formation of the control volumes. So, so this is for case 1 u is 0.1 meter per second, and for case 2 2.5. So, as you see that the velocity is very much increased. So, convection term will dominate into it in this case, and then accordingly Peclet number will also change. That also is a function of dx also. So, if you change the number of points or number of control volumes, that way also percolate number is has the effect anyway. But we will start with having the 5 control volumes. So, we will divide this whole domain into 5 control volumes. So, divide the domain. So, this domain is divided into 5 control volumes. So, if you divide this and length is 1 meter. So, in that case the delta x becomes 1 by 5. So, that is 0.2 meter. So, once you have delta 0.2 meter, in that case you can have the calculation of other things like f is rho into u, then d will be tau upon dx. So, based upon the value of tau you can have the value of d also being calculated. You will have the value of Fe or Fw, that will be equal to f, and similarly d equal to dw, that will be equal to d, that is everywhere. Now, what we need to calculate in this case is that you have you will use these differencing schemes and you will be calculating. Now, what we see that when we use the central differencing scheme, now in that case we know that you have you get one expression for phi p in terms of the phi w and phi e, and also you have the source term also coming to picture. So, what we will do that next. So, your domain will be looking like this. So, you will have this point on the side. So, this will be x equal to 0 and this will be x equal to 1. You have this point as A and this point as B. Now, you have 5 points. So, 1, 2, 3, 4 and 5. So, you will have 5 control volumes will be formed like this. So, control volume is formed so that the boundary is matching with the the outer boundaries. So, that way you form these control volumes. You are getting this is how you are getting the control volume. So, we get these 5 control volumes. Now, what we have already studied so far earlier, that we will have the similar type of expression for for the nodes 2, 3 and 4, whereas for 1 and 5 we will have the somewhat different expression because of the because of finding the value at this point. So, if you take the node 1, at node 1, if you use node 1, you will be having the expression, that is Fe by 2 into phi e plus phi p, and then you will have the expression that is on the other side. So, you will have f a phi a, and that will be equal to, again you will have the value at the east. So, it will be phi e minus phi p, and then you will have d a, that will be phi p minus phi a, and phi a value is known here, and that is anyway given. So, if you use those values, so accordingly you will have the expression for this. Now, similarly if you go for the node B, you will have the B point that will be coming out. So, for node 5 you will have the FB phi b, then you will have minus FW by 2. So, that will be phi p plus phi w. So, that because you are having this as, suppose anyone, this is 1, this is 2 or so. So, you can have this as the waste, and then you will have this is the waste phase, and if you take this, so this will be your P, and this will be your east phase, and this will be your east node or so. So, FB phi b. So, once you go to the fifth node, in that case you will have that FB. So, FB phi b minus FW by 2, and that will be phi p plus phi w. It will be coming as dB of phi b minus phi p, and similarly you will have the dW and phi p minus phi w. So, these are the two equations which you get at the extreme 1 and 5, and at other points you will have the AP phi p will be AE phi e plus AW phi w plus source term. So, you will have at other places you will have AP phi p, that will be AW phi w plus AE phi e, and then you have the source term. So, what you see, if you do the rearrangement, you get the expressions for the or for every node, node wise you will have the value of AW, AE, AP, and then you have SP and SU. So, if you rearrange them, you will be getting those values. So, if you do the rearrangement, you will have the node here, and similarly you will have the AW, then you have AE, and then you have SP and SU, that is your once you linearize the source term. So, for node 1 your AW becomes 0, AE becomes D minus F by 2. Similarly, you will have the SP as minus of 2D plus F, and then you will have the the source term so SU, that will be 2D plus F into phi A. So, that will be there at the node 1, and similarly at node 5 you will have D plus F by 2, and this will be 0, this will be minus of 2D minus F, and you will have 2D minus F into phi B, and that is because of the boundary conditions which are imparted. If you go for by working on that equation, so you will get this expression, and for 2, 3 and 4 you will have the expression, that is D plus F by 2, D minus F by 2, and you will have this 0 and 0. That is what the common in that AP phi p will be A W phi W plus A phi. So, that is what you are getting D plus F by 2 and D minus F by 2 in these two cases. Now, if you employ the boundary conditions, and if you go for the case 1. So, suppose for case 1 where you have u as 0.1 meter per second, and as you see that your F will be rho u. So, it will be 0.1. Similarly, D will be tau upon dx. So, it will be 0.1 by 0.2. So, dx is anyway 0.2, because you have length is 1 and there are 5 control volumes. So, it will be 0.2. So, you will have this is 0.5. So, in this case you can have if you go for these nodes, you will have the value of AW, AE. So, once you know the value of D and F, so from here you can get these value of the these coefficients, and then these coefficients will be put in terms of the matrix. So, you will have so if you take the if you try to find the node, and that will be node will be 1 2 3 4 5. So, for 1 AW is 0. So, anyway your AW becomes 0. Similarly, for 2 3 4 and 2 and 3 and 4 it is D plus f by 2. So, D is 0.5 and f by 2 is 0.05. So, it will be 0.55. So, 0.55 will be there for these 3 numbers, and then for fifth it will be D plus f by 2 again. So, it will be 0.55. Similarly, if you go for AE, so you can have the calculation of AE again. So, this will be D minus f by 2. So, it will be 0.45, that will be 0.45 also. 2 3 4 it will be 0.45, and then last will be 0. So, then if you go similarly you go for SU. So, SU also you can have 2D plus f into phi a, and phi a you know. So, accordingly you can have the values. So, you will have the values like 1.1 phi a, something like that, and so that is SU. So, 2D plus f, 2 into D, so 1 plus 0.1 1.1 phi a. So, that way it will go, and then for the 2 3 and 4 it will be 0 0 0, and similarly in the end you will have minus 0.9, and similarly you have SP. So, SP will be again. So, you can calculate these values, and you will have the different values that will be for SU it will be minus 0. So, this will be 0.9 phi b, and for SP you will have minus 0.9. So, you can what I mean to say that AP will be and you can get AP as AW plus AE minus SP. So, that can be calculated from here directly. You can have the values of the AW, AE and the SP. SP is minus 1.1. So, accordingly you can have the value of the AP. Now, what do you mean to say that? So, AP will be coming as 1.55. Similarly, you have 1 here, you have 1 here, and 1.45. So, that you can calculate yourself, and you have one values in that table. Now, this leads to the formation of a matrix, and then that matrix basically you have all these values. So, you will have the values accordingly you have as you go, and then that will be multiplied with the phi 1, phi 2, phi 3, phi 4 and phi 5, and accordingly you will have the values. So, if you take the phi a as equal to 1. So, for phi a equal to 1 and phi b equal to 0. So, you will have again the expression you will have 1.1 0 0 0 and 0. So, accordingly you have to get the solution of this phi 1, phi 2, phi 3. So, phi 1, phi 2, phi 3, phi 4 and phi 5 is computed, and you get the values using the central differencing scheme. Now, similarly, now the thing is that the problem is that we have to know that how much it is getting closer to the analytical solution, and when it was compared with the analytical solution. So, analytical solution is anyway given for this, and when it was compared with the analytical solution. So, it was seen that there is a match in this case. So, it comes like this. So, you will have phi value 1 here, and if you if this is you are getting with the central differencing. So, with exact also it matches if you are taking the central differencing. Now, what is seen, the problem is here is the problem which can be seen later will be because of the case 2 which we will be dealing. Now, if suppose we deal with the case 2 now in this case. So, if you go to the case 2, in that case u becomes larger. So, in that case your u becomes 2.5 meter per second. So, your f becomes rho u, that is 2.5, and d will be tau upon dx. So, it will be 0.5. Now, if you look at the Peclet number f by d. So, f by d will be 2.5 by 0.5, that is about 5. Now, in this case again you will be getting the same matrix, and if you try to further solve. So, in that case and if you try to compare it with the analytical solution, the solution is seen to be, the analytical solution is seen to be here. So, you have phi here. So, one is there, and on this side you have a distance. So, on this side distance also it is 1. Now, in this case this is your exact solution, and if you try to do it through the central differencing for this condition, the result which is found is basically it comes like this. It is reported by in this manner. So, what you see that this result is it is very much far from the exact solution. So, the value is somewhere under predicted and it is over predicted like that. So, there is suiting of these results, and this result is showing that when you have a convection dominated flow, in that case your this what you see is that it is not able to predict properly because of the flow. So, its inability is there of the central differencing scheme to predict the flow in that case. Now, what you can what has been seen that if you are solving this problem by taking delta x to be smaller, or if you take, suppose you take the case 3 with 20 nodes. So, with 20 nodes what will happen, that the width delta x, control volume width will be smaller. So, the delta x will be so earlier you had the you had the delta x 1 by 5 0.2. Now, delta x becomes less. So, it will be 1 by 20. So, it will be 0.05. Now, in this case if you do that analysis, and if you can further find the values, you write the matrix and solve it, what has been seen is that your equation in the same same result was seen to be. So, if this is the exact, now in this case it was found to be very close. There is not complete matching at all the point, but it is very much close it was seen to be. Now, that is because you see that the Peclet number, that was f by d. So, f into dx by tau, and if you see the the value of the Peclet number, it becomes very small, and in that case even so even for the higher velocity case of 2.5 meter per second, you are getting very close result to the to the analytical results. So, that is the effect of the number of nodes which you are increasing, and that way you are getting a closer result. Now, same problem when it is done with the other higher order schemes or other schemes like the upwind scheme. Now, in the case of upwind scheme, even with the smaller nodes and also with the for the for case 1 where the velocity is very small, it is said to seen to be matching, but even if when we are where you have the large shooting seen in the case of larger velocity values, the upwind differencing scheme seems to be matching, because matching with the analytical close match is seen in the case of the upwind differencing scheme, because when the Peclet number is higher, in that case the upwind differencing scheme will work better, and with the lower number of grids also the closeness which is maintained will be smaller. So, what has been seen? So basically what we have seen in this lecture, that you can try with the other differencing schemes and just see that how your result is matching with the analytical value which is which has been given. So, so basically the analytical value, if you look at the problem there. So, anyway analytical value it has been you have to compare the results with that analytical value, and that is basically given as phi minus phi naught divided by phi L minus phi naught. That will be exponential of rho u x upon tau minus 1 divided by exponential of rho u L upon tau. So, and then minus 1. So, that way you have once you get these numerical results, and then you compare with these analytical result, and then you can compare and see that how the other differencing schemes work, and how the effect of convection can be seen predominating, and then you feel the need to have the use of these other differencing schemes, because your those conditions of the transportiveness, boundedness and conservativeness needs to be satisfied, and that will be governed because of there are many other factors like the coefficient value needs to be positive, then there has to be boundedness, there has to be consistency in representing the conservativeness and all that. So, I hope that you will be having some more zeal to look into this aspect and go and study the different aspects of the other differencing schemes, which we will be mentioning while dealing with the flow analysis in the turn days. Thank you very much.